Our guest tonight is not just a physicist. He's a master of turning the weirdest parts of the universe into something even your child can understand. He's a best-selling author. He's an author of Cosmic Bullshit, and which was his latest book, and his Quantum Bullshit, and of course his Baby Universe series. It's our absolute pleasure to introduce the always witty and always entertaining and brilliant Chris Ferrie. Did I pronounce your name right?
Yeah, that's perfect. Thanks.
Good. I'm always like a bit when it comes to names. I'm really bad at it. I don't know why I do the intros. You should be doing this.
No. You're doing the intro. Right, Chris. So your latest book is Cosmic Bullshit.
Yeah.
We both finished it. Loved it, by the way.
Awesome book. Really awesome.
The thing that struck me the most at the very beginning was just how much topics you touched on in the book. It was amazing because through the years, like learning about cosmology is my hobby. I love it. I go deep into like 1 week I'm reading or watching videos about black holes. The other week is something else. I think you touched upon basically every single point there is to talk about. That's like at least widely known about cosmology. So that was amazing. That struck me really when I finished it.
Yeah, I think when science itself, it seems, especially physics, seems complicated, but it's actually a remarkably simple story. And I think oftentimes when we pit science against pseudoscience, we think that pseudoscience is a simpler story, right? Like you think, okay, well, is the Earth flat or not? A flat Earth sounds like a simpler story than the understanding physics in gravity and Einstein. But when you start to go down the rabbit hole of pseudoscience, you have to believe all of these like disparate things, and they don't connect together really well. And so you have like these weird connections, threads to try to maintain this like giant worldview that contains all of these disparate conspiracies. And when you compare that to physics, physics is just really simple, right? As you said, like, yeah, there's really cool and awesome stuff, but there's not that much of it. You can fit it all into a book.
Yeah. To me, it's always amazing when those stories kind of connect to each other, and it all needs to fit this larger puzzle. Especially, it's especially interesting to me in terms of mathematics. It's just like we play with numbers, and somehow we get to like using different methods. We come to same conclusions, the same like I don't know what ages of universe, ages of Earth, and it feels like we're literally building a puzzle, but it's also playing with numbers in terms of math. So that part is super interesting to me.
Yeah, that's exactly right. And the numbers are really just stories, right? It's a different way to tell a story. We create a model. We know that the model isn't exactly reality. And we found that like the most useful models we create are ones that incorporate mathematics. And then we use those to make predictions and fit data. As scientists, we understand that if those models aren't exactly right, but they're useful. So it's like a good working assumption to go with that. But when you think about black holes, I mean, only until recently, like these were theoretical things, right? We talk about them as if they were real. And until like we could really, in a sense, prove that they exist by like taking photos of them, uh, yeah, we had to say something. And so we talk about them as if they're real. And oftentimes we don't say to the public that these are working assumptions. And I think the most the biggest one now, right, is like dark energy, dark matter. That's an idea, like it's a model. It seems to work. It fits with our other theories pretty well, but we don't know really what it is. And we tell these stories. We write documentaries about them. We write research articles about them, but it could be something that isn't even real.
Yeah. There was one you just reminded me. I think not even a couple of days ago. I saw a podcast where they were talking. They were applying some mathematical method to black holes, and they started constructing this whole new idea that black holes are somehow mirrors. And I didn't go too deep into it, but interesting thing about it was they removed the necessity for like dark matter, necessity for dark energy. Are you aware of what I'm talking about, or
I
is
don't know
that
the specific one, but I know that there's lots of modifications to gravity, like Einstein's equations, Einstein's theories, that show all of the data that suggests that there is something else out there fits with a slight modification or is consistent with uh, the current kind of standard model of cosmology.
so? At
There's
what
like there's
point?
like thousands, like there's thousands of ideas for every one
Yeah,
that you see talked about on the podcast. There's like 1,000 more.
yeah. This one was just interesting to me because it kind of removed the necessity for some of these, like I would call them placeholders, like dark
Hmm.
matter and dark energy. So it was just interesting to me. I remembered it, so I wanted to ask you about that. But while on the subject, how do you um like at what point do you look at somebody's new model or solution to something and say like, okay, this is something that we need to look at? Like at what point does it become more than somebody's idea and kind of starts being looked at for by the majority of the science community?
That becomes rarer and rarer as we go because the big problems that people work on aren't, they're not like the ones of the 20th century. So, an analogy I like to use is like a physical explorer, like someone who gets on a boat and goes and finds new land. Such a thing doesn't exist anymore, right? We have
Mhm.
satellites that have mapped out every inch of the planet. So you can't be an explorer and go find new land. Uh, and it's like that in physics. There isn't going to be another Einstein, if there even ever was an Einstein, in our kind of caricature of a lone genius. Science has become this collective endeavor, and where people can still make great contributions and finding new territory, in a sense, in this metaphorical map, but it's not going to be as visible, say, as a new island, right? It's going to be much more nuanced, but equally important. So this idea, I mean, there's some like serious scientists that are looking for what you might call a theory of everything. Uh, I'm of the opinion that such a thing doesn't exist, and even if you found it, it wouldn't be exactly what you thought it was going to be, and wouldn't be very, very useful. Uh, my philosophy is not one where I think that there's going to be some ultimate aha moment where the truth is revealed, right?
Mhm.
So we're going to find new ideas, new theories. Those have to fit with the ones we have, right? And we have so many that it really constrains like how surprising something new could possibly be.
Yeah. Now, where's string theory at? Because I knew it was like at once projected as this like all-encompassing truth, and didn't it like take a little bit of a fall in recent years? Like it didn't exactly amount up to what people thought it would be.
Yeah, well, hopefully it's relegated to basements of physics buildings. I think it's mostly dominated by mathematicians now. I don't think it's taken seriously by practicing physicists anymore. Um,
Mhm.
yeah, it's a good question. I think I, you're praising, yeah, certainly in a sense it's taken a downfall. There's been a lot of bad press about it, right? There's popular science authors have written really negative things about string theory. That certainly hasn't helped it. They, you know, I think they're right in a sense. It was oversubscribed uh, for what it could possibly have provided. What there's a there's good, not maybe not good, but there's like reasons that you can understand why it became so popular, right? Because it was, we were in a time when the the kind of philosophy of reductionism was in its heyday, right? we got so much value from thinking about how things work by breaking them apart and understanding the smaller pieces they're made of. But I would say in the last 10, 15, maybe 20 years, especially, that philosophy has started to lose its power, right? We we can't break things apart anymore. And this kind of like new science of complexity, network theory, these sorts of things, where you understand that the no matter how much you break up something into smaller pieces, or how much you understand the working parts of something, when they come together as a whole, you're not going to be able to describe or derive some of the properties that you see. Like, uh, a modern example is just neural networks, right? Like we built these things from scratch. We know what a machine learning algorithm is. We know what a neural network is. It's a bunch of artificial neurons. They're stacked together in layers. We can see all the numbers that are inside them, yet we can't answer the question, why when I type something into ChatGPT did it give me that answer, right? Even though we can just look at all the pieces that it's made of. So it's not like a kind of you want to be cautious when you say these things. There's not like the whole is greater than the sum of its parts. Like the neural network is just all there is. But it's impossible in practice to be able to derive these higher order behaviors from an understanding of the smaller things. And so string theory was like, it was following along this path of reductionism. Like, okay, well, we split an atom and we found out what was inside atoms, and that helped us understand all sorts of things. So now let's split the quarks that are making up the atoms, and it'll give us even more power. But it turned out that, well, that's not right for many reasons. One, no string theory or any of its variants have given us any predictive power. It hasn't even given us any conceptual advantage. And at the same time, we started to realize that we had this like new philosophy and this new like really rigorous science of complexity and network theory that has borne more fruit than any sort of reductionist approach.
Yeah, that's a really interesting take. Because whenever I would listen to somebody talk about these like all-encompassing theories, nobody ever, at least I didn't hear anyone like to take that approach. Everyone is either talking about the existing ones or talking about possible future ones. Nobody said that that's maybe not the best way to look at that.
Well, yeah, and it's understandable, right? So you can talk about what exists now, and it's a relatively simple story, right? There's quantum mechanics and there's general relativity, and uh, they don't really mesh together perfectly well, but in some approximation, uh, which we call quantum field theory, that describes every observation that we've ever done, right? So we have a theory essentially of everything that we can see now. But then there's some places like what's inside of a black hole, what's at the singularity of a black hole, what what happened in the first few instants after the Big Bang. Those are areas where our models don't make any predictions, so they break down. So there's a nice simple story for what we believe or what we take as true now. And the future ones are obviously speculative, and when they're talked about, they're not talked about in great detail. Like they often have to incorporate far more complicated mathematics than we have now. But we tell them in metaphorical terms, so they end up also being simple stories. And why do those resonate with people? Why do people talk about them? Why do people that do talk about them get more playtime? Is because it's simple and people want simple stories. Like they don't want a complicated story. So what I'm saying is no, it's far more complicated. Um, and I can't even describe it to you because it is complicated. Right? We have disparate theories. They're all wrong in some sense. We patch them together. They work in their various regimes, and more moreover, that's the way it has to be, right? There is no simple story, and that doesn't resonate with most people, right? So they
Yeah.
started with uncertainty, and I've given them more uncertainty. When what they came for was like a sense of control, a sense of identity, a sense of feeling that somebody has it figured out, even if it isn't me. And the fact is, nobody has it, and nobody will have it figured out.
I gotta jump in here for a second. I love that. I also love that in your book so much. Like, I like it how you introduced moments of psychology a lot. Like when you were like playing a devil's advocate, when you were like playing the astrologist, I loved it. Because it was like you were talking like so widely, and like that was such a general story that it applies to like 9 out of the 10 people. And I loved it, and I like it. Like I really like that in your book, like where you introduced history, you introduced psychology, you even had moments of philosophy. I really loved it because it wasn't your like average science book where you just like open it and read. Like it was actually something I was driving while I was listening to it, and I actually had like what was it like 200 300 miles trip, and I listened to the book while I was driving, and it went like this. It was actually really fun because it wasn't your average scientific book where you need to like sit and like focus on every word. And you made me laugh so many times, and it was like really a great experience. And I also liked it how you probably didn't do it consciously, but like I felt like shades of your baby university in that book. Like you were educating like all of us on much more than just the science that was your focus. Like you were telling us, like I laughed so hard when I heard the part about the guy from Oklahoma who tried sacrificing a virgin so he would stop like I don't know what happening with a comet. I was laughing. I turned back that part like 3 times. Then I googled it to see if it actually happened. And there were some other moments as well where you spoke about some really really far back historical moments. You mentioned Gilgamesh. I was like I really genuinely enjoyed the book because it was much more than an average scientific book. And now that you said like you came here to look for certainty, and I gave you an even worse situation when you went out, and that was like I really like your approach to science where you're taking it down a notch so an average Joe like 99% of us can understand what you're saying. And I think that's like the biggest part of why your books are so approachable for me, at least. Like, I might not be the smartest person in the world. I might not be the dumbest. I'm somewhere in the between, and it works perfectly for me. It's like right there, something that I can take without any special concentration or anything that I need, but still I need to focus so I can get everything you're saying. And it was awesome, an awesome experience overall. Really, it was the first scientific book which I listened to. I don't read, I listen, that I could actually read or listen to without while focusing on it, but still being able to do something which doesn't require concentration, like driving. It was an amazing experience. Really, I really loved it.
Oh, great. I mean, that's obviously exactly what an author wants to hear. I didn't read the book. If you've heard the book and then now you're hearing me, you'll know that it wasn't me who read it. So Daniel
Yeah, yeah, we
Heddings
know.
read it, and he also read Quantum Bullshit. And he did such a great job with that one. I knew I had to get him back for this one. Yeah. So certainly when it comes to an audiobook, the narrator adds so much, right? So
Absolutely.
yeah, definitely have to give props to Daniel for a great read of that. Um, I think, yeah, I mean, secretly, I, the I want to teach people about things, and there's various reasons for that. Like one, I think it's important, but also the I think the most important thing for your own understanding, or the most effective thing you can do for your own understanding of a topic, is teach it to someone else. Right? There's this saying in medicine: learn one, do one, teach one. So you can't be a surgeon unless you've learned how to do surgery. You have to also do a surgery But even then, you still can't be a surgeon. You also have to teach someone else how to do a surgery, and then you can be a full-fledged surgeon, right? And I think you should apply that kind of mentality to anything that you want to do or learn. So I'm constantly teaching people, and not always directly. Like when I write a book, I don't imagine a specific reader, but a hypothetical set of readers, and it's a different audience every time, right? So I am kind of, I write about quantum physics all the time, but I don't just say the same things over and over again. I'm trying to teach it to a new audience, a new person, and that has helped me understand it far more than I could have if I was just trying to absorb information. Um, which is a weird, like, it's a weird thing for me to recommend, right? Uh, because, what I'm selling, ostensibly is books, but what I'm telling you is don't read books, write books. That'll be far more effective.
Yeah.
Yeah, well, not everybody can do that.
Oh,
Yeah,
you should try though. I mean, I couldn't do it when I started. I was terrible at it. And even now when I write, it's all on a computer, but I have a folder called bad ideas, and I even if I have an idea, I write it down, and I eventually, if I decide it's not a good idea, I stick it in there, and every once in a while I go there and there's a whole bunch of files in there, and I look at them, and sometimes I pull them back out and give it another go. But yeah, just writing things down, writing down what you hear, what you know, what you think, and then trying to turn that into something where you're going to explain it to someone else. Right? It you know, until you try it, until you do it, you won't realize just how powerful it is.
I touched a bit on it because like I do something similar. I do write, but I don't write books. I actually like that's my hobby, not my primary job. But like I write lyrics for music here in our country, and I do it pretty well. And like I do it with quite a few like major artists, let's call them that way, here in our region. So I do write, but it's a completely different ball game when you're writing a book. I actually tried it, and it's like it's really consuming somehow. Like I obviously wrote fiction. I
Hmm.
didn't try to write anything like that, but it's really consuming. Like it demands me to get in a certain like place in my mind where I close myself off from everything, and I need to close all the doors to the whole world, and I need to like be by myself and like going through my brain, and it's a really hard process. Like at least for me, it's something completely different than anything else I did before.
Yeah, I've never really tried to write proper fiction. I think that for me would be very difficult, but mostly because you have to have a context, and I imagine the people that write the best fiction are people that have also consumed a lot of fiction as well. So I don't read
Mhm.
a lot of fiction. I read mostly nonfiction. So the other, yeah, and that's another thing, right? When you try to create something, and whether that is a new piece of fiction or a new piece of music, um, you you have to work under the constraints of what what exists already, and like what people expect, right? So
Yeah,
you can't make it too different from what already exists because people aren't ready for it. So a lot of the children's books, a lot of them are what I call parodies. So they take like a theme or a an existing children's book and then kind of add science to the same theme. And that's worked really well because it it kind of conforms a little bit to people's expectations. Like so you have they have some expectations, and you deviate from that a little bit in the direction you want to take them. So if I want to teach people about quantum physics, then we start with a formula that already works, right? Like a pattern within a children's book or within like adult nonfiction, and then we modify that a little bit, and that makes it
yeah,
easier.
absolutely,
That makes it a lot easier.
absolutely.
I couldn't imagine sitting down and say, "Okay, now come up with a fiction story." I think that would be way outside of my wheelhouse. But I'm not. Once you once you're doing all these things and you build up expertise in various number of fields, well, I think the biggest thing that it grants you is confidence. So it's not like I don't think I would write a good book if I sat down and wrote one. But I also think that if I gave it a shot and spent, a few years trying it, failing, eventually I could probably do it.
I honestly think you would do good because that's exactly what I recognized in your book. Because like it doesn't matter if it's fiction, books, if it's music, it's whatever it is. If as long as it's not science, um, I think you need to have an artistic mind in order to write it. And if you're good at, in general, at art, at imagining things, you're going to be good at any kind of fiction writing. I think music is fiction writing as well because you're imagining a situation and you're talking about it. So that's why I actually think you would do good because like your book, even though it was a science book, it had those moments. It had those artistic moments where it wasn't. I didn't like for like even paragraphs. I wasn't feeling like I was listening to a science book. And then you take me back to the science, and I'm like, okay, so we're jumping ships here. We're going here. We're going here. So I think you would absolutely do great there as well.
Oh yeah, I mean, also the book was meant to be comedy, right? So I attempted humor in the book, and that's always dangerous. I knew at the outset that once you are talking about humor, you're never going to get something that pleases everybody.
Yeah.
So I was really kind of targeting us, largely a group of people that wouldn't be reading my children's books. So the children's books worked remarkably well for a large a large audience. So obviously people are buying it for their kids. People are buying it for their friends who have kids. Grandparents will buy it because they're going to read to their grandchildren. But it's also like about like quantum physics for babies, for example, is given as a gag gift. So if you have some, uh, your child is getting a bachelor's degree in quantum physics, you give them the baby book as a joke. So it's used as like a gag gift, and people like I've seen it being used in classrooms. So, on day one of a quantum physics lecture in a university, the teacher will bring it out as like an icebreaker. And the latest one was someone said they used it in a job interview, and they successfully got a job bringing my book into the job interview. But what it didn't work for was like I would say undergraduate physics students. So they for the most part won't have children, um, and will be sort of removed from that world of children's books and stories and games and things. And they also at that age are they feel like they know everything. Like they just took a quantum physics or like they took a physics course and they learned some new fact and now they think they know everything. And by necessity, these children books simplify things down quite a bit. And so when someone who's an undergraduate physicist looks at the book, they scoff at it, saying this is all incorrect and you're teaching people misconceptions, and they get really angry. So the the quantum bullshit and cosmic bullshit was largely for that audience I was really missing out on, right? Yeah, and yeah, I think the humor kind of aligns. I think probably with that demographic quite a bit, but it certainly doesn't align with everyone. Like
Talking about the humor
even
in your
just
books,
yeah, even just
I
putting
need to
swear
ask
words
you,
in
like, what's your deal with the crabs? What kind of beef do you have with crabs?
it.
Why did you keep killing them in the book? What's wrong with the crabs?
So there's a lot of like inside jokes in there. Um, that one was like it was like a meme from like 15 years ago. There was some cooking book, I think it was, and it was it wasn't originally in English, and it was translated to English, and there was a recipe for crab, and one of the steps in the recipe was to cut the crab's head off, and then it says afterwards, "This kills the crab." Um, so so then I just yeah took all of these like ridiculous scenarios, like the sun scorching the earth, and yeah, it's gonna kill feel the last breath
Yeah.
for sure.
Yeah, we were like talking like, and he was like, "What's with the beef with crabs?" And I'm like, "No idea. We're gonna ask him.
Yeah.
I'm
Yeah.
sure we're gonna ask him about it."
I did figure that there were some jokes that are maybe some demographic jokes, some inside jokes, as you said. Yeah, but
Yeah.
they were good. Like the comedy was really nice.
Yeah,
I
I put quite a few like little Easter eggs in there. Um, mostly kind of like 2000s internet culture type things, but I tried not to make it too obscure.
Yeah, I wanted to ask you because you mentioned that you built confidence, you acquired expertise in a bunch of different fields, and then you started teaching writing. But I want to, is it like for you today in terms of learning? Like as someone who did acquire this expertise in a couple of fields, and you acquired all this knowledge, how does it look? Do you still learn, and how does that look for you today?
Yeah, absolutely. So, your expertise grants you like the ability to do certain things, including teaching it to other people. But there's always ways to improve your understanding, right? Because you can go into a classroom and then teach it the standard way, and you find it works for 70% of the students, but you miss out on another 30%. So now you got to say, well, what is it about the way I presented it that didn't reach those 30% of students? And so you go back and you try to improve your understanding, or not even necessarily improve, but find a different way to approach it, right? Because when something is easy to understand and learn when fits, it fits into your existing knowledge. Like it's a story that extends what you currently know and what you currently understand. That's, by the way, the the best part about teaching, like in practice, is that when you if you have to stand in front of a group of students, then you better know your stuff, right? Because they're going to ask you questions, and the easiest way to do that is to have like your own story. Like you started from the beginning and you worked your way up to some uh, concept or whatever, and so it's much easier for you to conceptualize it and remember it if it's your story, right? So that's what I'm trying to give to students, right? To not to have them memorize a fact or uh, be able to regurgitate a concept, but to incorporate that into their own story. And everyone's story is different, so you can always go in a sense relearn the thing that you know. And there's the more you and understand, the more you can see all of the gaps in your knowledge. So if you think about a topic like quantum physics, you you might say, "Well, I don't know much about quantum physics. I've heard a few things, so there might be a couple dozen concepts I need to understand." But what you don't realize is like for every one of those concepts, there's 10 more sub concepts within that you don't understand, and within every one of those, there's 10 more, right? So there's always more to learn. And yeah, being an expert means I can tell you, off the top of my head, the broad story, but every kind of little detail, I haven't studied yet. So it's yeah, every day is still learning. It's just kind of learning at a finer and finer details of things. But also, you can learn other fields. So although I didn't do a degree in machine learning, I'm bringing incorporating that into my research and then learning more and more about that, right? So I'm at, the baby level in some things that I could learn about and interested in. So it's every day is learning. You become better at learning the more we do it, uh, and it becomes actually more and more satisfying.
Yeah, I don't think people often look at learning as a skill as well. You know,
Yeah,
I think
yeah, I agree. They think most people, and this is it's probably because of the way that it is taught in most education systems. And the reason it's taught that way is so that you can assess students. So it's taught in a way to give the illusion that there are a list of facts. In historically, those facts are in textbooks. So you give this mental picture to students that there's a whole library of textbooks, and if if you commit yourself to reading them all, you'll know all the facts. But that's just not how it works, right? So when you sit down, you take a course in a particular subject. There's a textbook. There's an exam at the end, and if you read the textbook and you get 100% on the exam, it's assumed that you know that field. But that's just not true, right? Uh, the the hope, even though that it exists in that way, which is very suboptimal, the hope is that at least by taking that as a target, you'll acquire the skills as you go along. But as you say, absolutely, learning itself is a skill that you can improve and get better at.
Yeah, I definitely agree.
Yeah, absolutely. And also, I mean, like, besides learning, also teaching is a skill, like, especially working with students. Because, like, as you said before, when you stand in front of them, they're like, I mean, we were all students. We know how that works. They like try to pick you apart as much as they can. So I think teaching is also a big, big, big skill that some people either have or they don't. Like, I realized that when I finished high school, which was really strange because I really didn't like physics at all in my high school and my elementary school. And then, like, after university, when I had spare time, I actually started reading books about physics and I realized I actually liked it. I just didn't have a good person to intrigue me and to get me interested in the subject. And maybe if I had a good person to work with me on that, like, it would be a completely different ballgame. Because, like, when you watch professors, like those I mean, we all saw those videos when you have like a professor like swinging a ball from his head, like waiting, he's not moving, not flinching. And that's an approach which gets, like, out of 100 students, like 90 of them are going to get interested in what they just saw. But if you just tell me, like, this is this x this is this times this, like, you're not really getting me involved in it. I'm just like learning it by heart so I can, as you said, so I can pass the exam and that's it. So I think teaching is also a huge skill that, like, unfortunately not many people who are actually teaching have.
Yeah, and I think it depends. Like, it's certainly there's huge cultural differences as well. So in most Western cultures, teaching is seen as a very sort of low level profession, right?
Hmm.
Whereas in many Eastern cultures, like that's like the highest you can get. Like if you go to like rural areas in China, you meet some they're like the most important person in the community. Whereas in Australia where I am, and certainly like in America, if you're a teacher, people ask why. Like why would you do that? Right.
Yeah, I know.
And then so they're not paid well, and so that doesn't attract the best people. You know, in a sense, it often attracts good people because it there are people that are so passionate about it that they'll do it in spite of the fact that people, you're not treated very well and you're not paid very well. I think it's from a societal perspective, it is the most important job, right? At least the way
Absolutely.
society is structured now. For me, the argument is simple, right? I'm gonna get old, and when I'm very old, I'm gonna rely on the people that are in school today. So I would like them to be very well educated, right?
Absolutely.
Uh, but yeah, people don't seem to see it that way. I guess that's too
And to
long
build on
term.
that, what you just said, like, I even heard like people saying, like, "Oh, he's a professor. If he knew how to do his job, he wouldn't be a professor. He would be actually doing it." And I'm like, dude, he's like, that. wh- what better way could he practice what he knows than being a professor? He's literally teaching others to become what he is. Like, that's such a dumb comment. Like, when I heard that, I was in disbelief. I was like, holy crap, this is.
That depends on, I think, from area to area as well. And certainly things have changed, and I don't want to get too cynical about it, but in a lot of universities, a lot of countries, university systems, it's become very bureaucratic, and academia itself, a large part of it is just a game. And once you create that game, you'll get people that do well because they're playing the game. And some of the ways you play the game well is you publish a lot of critical articles. And if you look really closely, I would say 80 to 90% of journal articles, academic journal articles, shouldn't be written. Like they're not, they have no value whatsoever. But because professors are evaluated on how many articles they publish and how many citations those articles get, they're incentivized to do this, right? So that very few, I think, are in what I would say the best mode for a professor would just be one of like, scientific inquiry. And when you have an idea and you feel like you have a good story to tell, then you write the journal article. But now it starts with I need to write a journal article. What can I write it about? And then often what you write it about is the easiest thing can be published. So there's, I think, in an ideal world, yes, um, you know, we need those people that have the freedom to explore their intellectual curiosity and who are very good at it to push the boundaries and then disseminate that knowledge. But in the society at the moment, it that has been like severely corrupted.
Yeah. I wanted to ask you about kind of an advice because it should be fairly obvious by now, but we are neither students nor experts in any of these fields. We are just really curious. That's it. And I can give a specific example where I took a fall. Like when I was reading your book, or no, sorry, it wasn't a book. I think it was, I watched one of your podcasts. And you said you basically debunked for me the entangled particles and how they can be used to communicate with faster than light speed. And I usually have a kind of like a feel if I'm watching videos or I'm reading something where there are lies and misinformations. But that one I somehow swallowed, and I was like certain that there's a thing. I didn't imagine, of course, that we'll be using them soon to communicate or anything, but I kind of took it as a real concept. So how would you, because obviously if you teach your students, that you have ways of like giving them your knowledge. But for us that are in between, we're neither students, neither experts, we're just curious.
Mm.
How do you have like an advice how to follow, how to get correct information, I would say?
Well, what you what you can do is like first kind of understand that uh what people typically talk about, especially in quantum physics, is metaphors, because the real thing itself is just like a mathematical model. So you might have a picture in your mind of what is an atom, but that picture will be ultimately wrong. It'll be some sort of metaphor. And scientists themselves use these as well. But when they go to make predictions, they revert back to like the math formulas, right? So the metaphors can help you like guide you in what calculations you need to do or what experiments you might set up or how you set up experiments. But at the end of the day, it is just the mathematics. So metaphors aren't bad in and of themselves. The thing that is bad is when they're presented as fact or they're presented as truth. So if you just approach it that way, you can say, well, thinking of entanglement as, a connection between particles that persists across large distances, uh, that might help you in how you're going to set up an experiment or how you're going to measure timing in the experiment. But at the end of the day, that's not really what's happening. And to describe what's happening, it's just a bunch of equations. that have no analogous thing that you can describe in everyday language. But that's the most difficult thing in quantum physics. That quantum physics itself is just a set of equations, and whenever we talk about them, we're going to be using metaphors or analogies that aren't literal. So even when I can't tell you what an atom is, but I can describe metaphors for how we might imagine them and talk about them that may work in for some purpose, but ultimately isn't the real thing. That is probably also true to some extent with everything, but there's just a huge discrepancy between the mathematics of quantum physics and the mechanics of the everyday world that we're familiar with, that the analogies will break down very quickly. Whereas if you're trying to describe something in biology, you might use like a mechanical analogy. Like, oh, this particular protein works like gears in an engine, and you picture the gears moving. That's not exactly what's happening, but in the biological system, but it's close enough. In quantum physics, that the gap is just enormous. So it's really hard to talk about because there isn't a very straightforward analogy. But, yeah, so it's hard. Yeah, it's hard. But I'm not saying that we shouldn't talk about it, right? Because I think, a- as you evidence, there are people that are curious. So we need to be able to sate that curiosity. We don't want to, you know, just tell people it's too complicated. But we also have to be careful not to give the illusion that these metaphors are true.
Mm-hmm.
Yeah.
Can I build on that just for a
course.
second? What are some of the most common misconceptions you encounter when talking with people about quantum physics in general? Like experts, your students, whatever. Like, whoa.
So with quantum physics, you have the core concepts that are often discussed are entanglement. That's probably the most complicated one. And the idea that what entanglement means is a connection, like a physical connection between things that persist across large distances, and it's such that when you manipulate one thing on, say one side of the world, it instantly affects what's happening on the other side of the world. That is absolutely not true. Um, it's not even close to being true. It it Yeah, it's just that's kind of how people have decided to describe it, with for lack of a
That's how
better.
I understood it. Like, that's
Yeah,
literally how I understood it.
but
Literally what you just said.
the a, a a better analogy. So it works closer to the right way to understand quantum, like quantum entanglement, is as a correlation, and I find it quite funny that correlation seems like a complicated concept to people. I mean, it's a long multi-syllable word. All of its synonyms also are long multi-syllable words, but it's like a very simple concept, and it's how we navigate the world. Right? Well, the whether it's raining is correlated with whether there's clouds in the sky, right? Like the information that's at your location on your screen is correlated with what's on my screen. That's how we can have this communication, right? So correlation is everywhere. It's how we navigate the world. And the information that describes quantum things like atoms and fundamental particles can also be correlated. But that information is encoded in a different way, so the correlation is mathematically described differently. But that's all it is. It's just correlation. So if I say I take this the example you often hear, if you hear about a real kind of example, would be I take two particles and I manipulate them in such a way that some internal degree of freedom called spin, which could point up or down, is correlated. So when I separate them, I bring one to Toronto in Canada, and I keep one here in Sydney, Australia. And then I look at one and find that its spin is pointed up, then that immediately forces the other one to point down. Now, here's a situation that's more analogous to that, right? Suppose instead of quantum particles, I just took two boxes and took a pair of gloves and put one glove in each box and kept one here in Sydney and sent one to Toronto. When I open the box and find the right glove in Sydney, does that immediately force the box? Like I instantly across that distance, I know that the other box has the left glove, but is it being forced that way? No, it's just information, right? So
Yeah.
a better way to think about this quantum stuff it's all just information, right? And nothing physical is being transferred around. It's
How
just
do
our
how,
yeah.
sorry for interrupting. How did people get? Because I understand fully what you're saying, but somehow I think the biggest misconception that somehow got introduced there is that you can manipulate that spin, and then if I change the spin of this one, like in Canada, the other one will also change the spin, so they're opposite again. That's
Yeah.
the part I don't know. How did that get in there?
Okay, yeah, okay. So we can go down the rabbit hole. So this example that I gave you with the gloves is what's important about that example in any sort of physical object is that I or somebody put the gloves in there. So somebody knows which one has the right glove and which one has the left. And so you might try to say, well, here's the mathematics of quantum mechanics. Here's what happens if you actually did the experiment. Maybe what's really going on is that there are some variables that we haven't discovered yet that would tell us which one has the spin up and which one has the spin down. And it's just that if you try to come up with any theory like that, it doesn't work. So in the quantum case, you can't say that one of them I know was spin up and the other one I know was spin down each time you do it. So there isn't a predetermined state for each of them. So when I have my atom here in Sydney, it's not as if it was going to be spin up the whole time. It's every time I do the experiment, it's randomly spin up or spin down, and there's no way for me to know which it was. So it's almost like the spin is determined in that instant. So if the spin is determined in that instant, the other one must have been determined in that instant as well. And since I get to choose when I do the experiment, I seem to be forcing the other one. So that's kind of like if you want to follow like a conventional logic and have a classical picture of what's going on, you're forced to this conclusion. What's wrong is like the initial premise, right? That I could have assigned a spin individually to each of these particles. So if I don't make that at the outset, then I won't be forced to conclude that my choice of when to do the experiment forces something somewhere else in the world to take on a value. It's just that we can't in a conventional sense assign predetermined values to the properties that quantum things display. And that gets into a deeper question because having predetermined values is what we conceive of as reality. Like reality is there, regardless of whether I'm here to do a measurement or not. That's what we think of as reality. Like if if I cover my eyes, you don't cease to exist, right? You're still there, and you have all of the properties that you had before I covered my eyes. With quantum, with a tiny atomic level things, it matters how we interact with it. And so what we choose what property we choose to measure, in a sense, defines what will happen. And, I use the word choice, but again, that's another, it's, it's just something like, it's everyday language that we're kind of forced to use because we don't have good language for it. It's not as if my, my free will determines what reality will be, but how I define the experiment, in a sense, sets what can possibly occur. And that's the real lesson, I think, ultimately, kind of the deepest lesson of quantum mechanics, is that reality isn't what we expect it to be from our everyday interactions with the world. That there's a world out there, and it just operates independently of us. At some point, to try to get information from the world, we have to interact with it. Right? Um, an analogy might be, so when we look at things, right, what's happening is that light is hitting the object and then bouncing off the object and then entering our eye, right? That's not passive interaction, right? Like light carries momentum; it hits the object. For things that are large, like a table or chair, it's not going to affect it very much. So for all practical purposes, we can treat the chair or the table as if it always existed and it isn't changed by us looking at it. But if you have something that's about the same size as a particle of light, then look, what does it mean to look at it? If to look at it means I need to shine light on it. But if I shine light on it, I'm going to affect it. Right. So at the very fundamental level, our interaction with the world, for us to get information about the world, forces us to interact with it. And that interaction isn't passive. We have to do something to the world. And and so we can't just assign predetermined values to things as if they would exist no matter how we ascertain information from it. I think that's the most important lesson of quantum physics. So if you take that on
Holy shit.
board, then yeah, in a sense, yeah, don't yeah. So in a sense, reality doesn't exist.
Yeah, what are all the ways that we can actually how to say, not measure but like observe something? Obviously, yeah, you explained light, but I know like we also look for were there like muons or something, or like gravitational waves? Like what are the ways we can observe something other than light?
Well,
If
everything is sort of
that's a correct
indirect in
question.
that way, right? So we like detecting like particles in what the in CERN, the Large Hadron Collider, muons, cosmic rays, those super things. What we observe, well, nowadays is just kind of abstract data, but originally it was tracks of particles. So maybe you've seen a cloud chamber in a science museum, or you've seen the pictures of particle tracks. So what's happening is that um, something that's not visible to the human eye comes in, and it is not interacting with anything, and then at some point it interacts with air molecules or whatever's in the cloud chamber, and then that creates a condensation site, and so water or whatever it might be condenses, and then that becomes visible because light hits the condensation cloud and then comes to our eye. So we see like a track of condensed, clouds or whatever, and we, in our mind, we picture that as like a muon or an electron or some other particle that's taken that path. But that's not actually literally what we saw, right? The I earlier I said you can't see atoms, but there is a sense in which you can. So if you get a particular kind of atom and you shine laser light on it, it forces like a transition of its energy levels. And when it moves between energy levels, it lets off other light. So with a microscope, you can see individual atoms, but you're not seeing the atoms themselves. You're just seeing the light that it gives off after it's being illuminated with lasers. But that's like probably yeah, the smallest thing you can see, albeit indirectly with the human eye. But all of these things all of these things are indirect. And what's amazing, and again, is far more complex than I can describe or even understand, is that we we um we take all of these uh we take all of these things and we create like a consistent story, and they somehow fit together, right? Uh and that's sort of I think the magical part about it, that it all kind of fits together.
Yeah, I get it. I had one question also, because I think, as far as I know, quantum computers also kind of have to be, the individual qubits have to be like protected from interference from other particles and stuff. And like a part of it, it was also cooling it down to like near absolute zero and stuff like that. Can that ever uh, come to like a normal household as a computer? Because I don't see a way how those kinds of conditions can ever be uh, like replicated, so a quantum computer can be used as a normal computer ever.
Yeah, so I think there are, there are lots of there are lots of like areas of physics where you think things happen in a way that is so foreign to us. So we might be able to find a particular configuration of matter and energy that is inherently protected, where we don't have to like cool it down to absolute zero or put it in a vacuum chamber. So I mean, the reason we do this is, again, because the environment of like a quantum computer chip, which, let's say, contains individual atoms. So the chip is trapping individual atoms, and the computer itself works by manipulating these individual atoms and trying to get them to do calculations. Now, obviously, we can't shine light on them because, again, as I said, the light carries momentum, and that kicks them around, and that ruins the computation. So it has to be sealed. So if you picture like if you Google quantum computer, what you'll see is the inside of a quantum computer, but maybe one of the image will show the outside. It's literally a black box. So light obviously can't, it's not like a gaming computer where you can see the inside of it. It has to be, no light can shine on it. Um, but you have to remove all the air as well, right? Because air molecules can't be bouncing around hitting it. And there are, lots of other things in there as well, like e- even stray photons, cosmic rays from the sun can come in and hit it. So you shield it from that as well. So you do all these things essentially to shield it from any environment, which is effectively trying to observe it. So that's sort of the catch-22 of quantum computers, is like we we want to remove every possible interaction and environment from this thing. But at the same time, we have to interact with it to tell it what to do and then get the answer out. So it's this double-edged sword. So that's kind of like the huge challenge, the engineering challenge, is to on one hand protect it, but on the other hand, you have to interact with it. Uh, but the more we understand about physics, the more we're able to create exotic states of matter that may be inherently protected. So you might be able to put it in a warmer environment, or it's something that doesn't interact with light. Uh, and that's what will have to happen if he ends up in a household. Is it can't be, as you said, the way we're doing it now, but the more we understand about physics and these engineered systems, the more likely it is we'll be able to overcome these challenges. So there's just yeah, there again, there's so much that we don't know, that I and that makes it difficult to predict exactly what's going to happen in the future. There's the famous quote from the CEO of IBM in like 1948, when he said there'll never be a market in the world for more than 5 computers. And well, I can see in the video there's probably 6 or 7 sitting in front of you right now, right? So
Yeah.
uh, making predictions about the future is a terrible idea unless you really want to be wrong. But what you can predict, I think, with certainty is that surprises will come. Something will come along that we wouldn't have been able to predict today, and that will provide a new idea, a way to create computational devices that operate at that scale. And yeah, I'm it can't happen the way that we're doing it now, but I wouldn't be surprised. I wouldn't rule it out that you have like something doing quantum computation in a wristwatch or something like that. But it's beyond. If I had to bet, I would bet it's beyond my lifetime.
I need to build on that again. Like, how would you describe what the qubit is, really, without using the word bit?
Without using the word bit? Oh,
Yeah.
I see. Well, I mean, that's hard because what it stands for is quantum bit. um,
Yeah,
So-
that's
so-
I'm trying to get it for like us who
Yeah.
are not that much into it, to like get us to understand an average guy.
okay, let me describe it with the word bit first, and then we'll do it without the word bit. So a bit is the fundamental unit of information, right? It's a 1 or a 0. So a switch, a light switch. There's lots of physical systems that can represent essentially two possibilities. So something that can only represent one possibility, you can't encode information in that because there's only one option. So if you have something that encodes two options, that's the smallest unit of information, and it's called a bit. So a quantum bit is the smallest unit of quantum information. So instead of a 0 or 1, or like one of two possibilities, it's represented as two real numbers. So real numbers, include like pi and the square root of 2 and negative numbers, right? So instead of just a 0 and 1, we're representing information now with all numbers that we have. So if you have two of them, that's sort of like the smallest unit. So you take these basically pairs of real numbers and you put them together, and that creates more complicated information. But the smallest unit is what's called the qubit. So I could have skipped the whole bit thing and just said a qubit is two real numbers,
Mhm.
and we can encode information in those numbers.
Okay, that makes sense. That simplifies. You just said you don't like predicting what's gonna happen because you're usually gonna be wrong, but I'm gonna ask you anyways. Like, I'm wondering, how do you see quantum computing revolutionizing fields such as healthcare, as economy, financing in general? How do you see it revolutionizing those things, those like fields that it doesn't actually have like direct entanglement with, but how do you see it like influencing those?
Yeah. So there's no definite like quantum algorithm that we know of that's going to solve like a real world problem, let's say, more effectively than conventional computers. There are quantum algorithms that we know are, would are much faster in a sense. And by faster, I just mean require fewer steps to solve the problem, right? Because the difference is I'm encoding information differently. You remember long division? Remember doing long division in school, where you have to divide two numbers and like
Oh yeah, of course.
you put the line under, and then you have to do like
Yeah.
some So that's not the most effective way to do division. Like there are other recipes for doing it with fewer steps, but you did it that way because it was easier to lay out on a sheet of paper. So different algorithms require different steps depending on how you set up the problem and how you encode the information. So it turns out like if you use this quantum information, you can do it with fewer steps. Like there's an algorithm that requires fewer steps to solve the same problem than if you had to encode the information with ones and zeros. It's not literally faster. Like it's not the difference between like a Formula One car and a, you know just a street car, right? It's that the quantum car gets to take a shortcut to the answer. Each step itself might actually take longer, but it requires far fewer steps. So there are some problems where we have quantum algorithms that we know for certain require fewer steps, but they're like obscure math problems. And we've not connected those problems to any like real world problem. So you have some obscure math problem. We know that a quantum algorithm can solve that efficiently, but nobody's bothered to like connect that math problem to, say, an everyday problem in healthcare or in finance, or in agriculture or whatever it may be. That's not to say that a connection doesn't exist. It's just we're so far from actually implementing the quantum algorithm because we don't have a quantum computer that nobody has had the incentive to go and actually do that. So the company's not going to do it because that would be like a 30, 40, maybe 50-year time horizon. And certainly academics aren't going to do it for no reward, right? So there's just nobody. It's not a problem that anyone has the incentive to do. But I think there's lots of if a quantum computer was turned on today, you would find all sorts of applications, within weeks and months, because all of a sudden you're going to have a lot of people trying to solve these problems. But there's just nobody there trying to solve them. But so that's one side of it. The other way to think about it is that it's an inevitability, right? So what defines progress in technology is more precise and finer control of the physical world. And that typically means fewer and fewer bits and pieces of it, trying to get the most out of the physical system. And eventually, we're going to get to the size of atoms in what we can control in all of our technology. And at that point, there's no difference between saying conventional technology and quantum technology. We're just doing quantum engineering at that point. So quantum computing shouldn't be thought of as like an idea similar to an app like ChatGPT or AI, where it's an idea that is an application of existing technology. Quantum computing is like the future of technology. It's the only place to go. Feynman said, "There's plenty of room at the bottom," right? Like that's where we're going, to the bottom. It's the only place to go. So it, the only uncertainty is like how long it will take. So it's inevitable. We don't know how exactly we'll solve specific problems in these like application areas in the real world. We have some rough ideas, but it will come, and when it arrives, there'll be lots of people trying to solve the problem, and it human ingenuity with this is probably one of the most powerful forces in the world. So I don't have any doubt that we will solve those problems. If you read about it in the news, you'll see lots of speculation about very specific application areas, like make the process of making fertilizer is extremely expensive, right? It uses vast amounts of the world's energy and water, computational power to try to optimize these interactions. So that's one area where you might be able to solve some of these computational problems using quantum computers, because you have to kind of simulate chemistry. And chemistry is basically just applied, physics. So rather than doing it with like effective theories and kind of coarse-grained and fuzzy models that aren't 100% accurate, but provide some information. If you could just model the system virtually one atom at a time, then you would be able to, in a sense, build chemical interactions in the same way we build buildings in virtual worlds before we actually go and lay any foundation.
Yeah. I wanted to ask you a little bit steering away from the actual science, because you also touch in your book about things like aliens and time travel and stuff like that. And as you said, people love to kind of imagine what quantum computers do. They love to imagine faster than light travel of information, whatever. What would you say is the, I guess, most preposterous thing that people have imagined that could actually turn true? Like whether it be wormholes or like close to light speed travel, or like time travel backwards in time. Like, what would be the most preposterous thing, but that you actually, this just not predicting, just like your feel that it could be true, possibly somehow.
Yeah. Well, I guess I think uh, one difference between a lot of these, right, you can kind of break it into two categories. One is category that requires new physics. Right? So time, if you talk about like wormholes or time travel, faster than light travel, that sort of thing, that requires a different theory of physics than the one we have. So that I think is ruled out at the outset. And then there are things that are uh, kind of very speculative, but don't really require new physics. So life elsewhere, and we can certainly imagine that. It's highly speculative because we have zero evidence of it, but it doesn't require any new physics for it to be true. So uh, personally, I think there are other planets elsewhere in the universe that have uh, probably some form of life similar to early life on Earth. Maybe even intelligent life, but it'd be so far away that it's irrelevant. Like we never could be able to communicate with it. Whenever you can be able to find evidence of it. It's almost like they would be existing different universes. Um, yeah, so I think that's probably one of the most speculative things that I believe could be true. But I don't believe that we'll ever find evidence, and it's almost with near 100% certainty, intelligent life has never communicated with us or visited our planet. That I think verges on requiring nuclear things. Like any way you imagine how that could have possibly happened, and the mechanics of it would force you to invent some new theory of physics that we don't right now.
Yeah, nice, thank you.
Oof. Okay. I want to go
But did
back
you
to
want it to
something
be
you
true?
said. No. I honestly don't know. In general, my approach is always agnostic, like to everything. Like I'm always like, we don't know, and like nobody can say if it's either like we have a lot of people who would love aliens to actually exist, and then we have a lot of people who are saying they don't. I honestly think none of us have any clue. It would be logical. I absolutely agree with you. It would be logical that they do exist, but then again, we have no proof, and until we have one, I'm not riding that hype train. Not until I see anything like some proof, a little one. But I want to go back to something you said before. I don't want to quote you wrong. You said reality actually doesn't exist. You finished on that, right?
Yeah.
So
Uh,
I want to go to something that's really intriguing to me. Like, what do you think about the simulation theory? Does that make any sense at all to you?
uh, yeah, I think I mean, it's a nice logical argument. I haven't. So the argument is like deceptively simplified. But like, I mean, right now we simulate physics. We create worlds like The Sims. Um, we seem to attempt to try to create video games that are closer and closer to reality. Um, Artificial intelligence systems are becoming close, like resembling more and more the way we speak and act, and interact. So it's it's plausible that we create some virtual world that is close enough to reality that an a programmer entity within it might have an experience, right? Um, and then, well, if it's equally as complex as we are, then it might create a video game within the video game, right? And so then it becomes like an infinite chain. And so if you assume like this infinite chain exists and ask yourself, well, what's the probability that I'm at the top of the chain and not just one of the simulations within a simulation? Then it should go very low, right? How arrogant to think you were the prime mover there. Um,
Yeah.
so that's like it seems like a really you know straightforward and simple argument. I've never really paid close enough attention to trying to dissect where it goes wrong. Um, it's probably you know to it's not inconceivable that the humans and the human brain, life on Earth, is the most complex thing the universe has ever sort of evolved. And, right. It started very simple. Things started to get together to create more complicated things and more complicated things. And we're at like we're at this point in the universe, we're at a point, reaching maximum complexity. So, the picture you should have in your mind is like, you take a cup of coffee and drop some milk into it. It's initially just a drop at the beginning, and at the end, it's like a uniform kind of mixture of coffee and milk. But in between, you get like these really complicated patterns and ribbons and things, right? So that's typically how systems go, right? They start very simple, they end very simple, and go through a period of like maximum complexity. So perhaps we are at the point in the universe where we're close to maximum complexity, and that maximum complexity happens to happen here on Earth and involves living beings. Now, in order to simulate that, might require so many resources that you basically need to replicate the thing that we're trying to model every thing. And then that would be essentially impossible. So say I wanted to create a virtual Earth, right, with people that are conscious. You might need a number of resources that essentially has you just replicate Earth, right? Um, so then it becomes. Then I think that's where that argument would break down, right? That the sort of the simulation argument is simply that in order to model this level of complexity requires as many resources as there are within the thing you're trying to model.
Okay. That was
But also, I don't think it's similar to the Boltzmann. Have you ever heard of the Boltzmann brain?
no.
No, actually, no.
So even like you imagine, so say like imagine a box full of air molecules, and so they're all kind of randomly spread around. But each individual configuration, like each lottery ticket, has the same probability. It's just ones that are kind of look random are more likely than ones that don't look random. So, the lottery ticket 1, 2, 3, 4, 5, 6 is just as likely as 1, 23, 37, 41, right? It's just we see a pattern when we see those consecutive things. So the configuration where like all of the air molecules just spontaneously end up in one corner of the box is a valid configuration. It's just highly unlikely. But, if you just left it there for an infinitely long time, eventually that would happen, right? It wouldn't be a
Yeah.
uniform mixture of air molecules. Eventually, they would all show up in the corner of the box. Now, take that picture and, imagine, the universe is just a bunch of atoms and they're just kind of uniformly spread out. But if the universe lasts infinitely long, then at some point in time, they'll get together and make something more interesting. Um, so you could say like this world, like our universe, was just a fluke. Like it's just one of these flukes that happened. Things just came together, and this happened in an infinitely long universe that doesn't have probability zero. So it will eventually happen. But for all of this to happen, it's certainly far less likely than just enough molecules to create a single brain in a sea of nothingness that is just imaginary for a brief instant. So uh, that's what's called a Boltzmann brain. Like
Mhm.
in just a kind of a uniform mixture of atoms, eventually they'll kind of spontaneously come together to form a brain, and they'll form a brain that has memories, a particular set of memories, and a particular set of perceptions, and that that will happen far more often than a brain that also has a body, and that will happen far more often than a brain that has a body and other brains around it that also have bodies, right? So, you know, again, if you if you believe that all of these things are possible, then the most likely scenario is just they're just like a brain sitting in space, imagining all of this happening.
Yeah, I have one more question. Because you mentioned like infinite amount of time, if you leave it there for infinite amount of time. And as somebody who's just curious about all this, the biggest problem I always had with like learning about science were those infinities. Because uh, tell me if I'm wrong, but I just want to like see how do scientists actually look at infinities? Because I get talking about infinities if we're talking about numbers, if we're talking about like some thought experiments, but in reality, unless I'm wrong, nothing we don't have a single example of anything being infinite. And then when people talk about infinite time or infinite universes or infinite earths with infinite us
Yeah.
having these conversations, but if we look at reality, not even black holes are going to exist infinitely because of Hawking radiation, or however space ends up like either expanding too much or contracting too much as a big crunch, whatever it is. Is it just me not being able to comprehend infinities, or
Uh,
are we actually expecting anything to be infinite?
well, yeah. So I guess infinity itself is just like it's a concept, right? It's not a number. So it just means increase without bound, or decrease without like. But uh, you have to be referring to like a sequence of things that never stops. Um, there isn't a specific one. Uh, and in physics, yeah, like if you take like a finite volume and you make some prediction, and the prediction seems to show like something is increasing without bound, they'll say, "Oh, there's an infinity," um, and that seems completely impossible. So we reject that, and that's what we hear about like black holes, for example, or the initial problems with inflation or the Big Bang, because what the theories predict at those locations is something that is, they say infinity, but what it means is like something is increasing or decreasing indefinitely, like not stopping. Um, we, I mean, we use mathematics that includes these things all the time because they work pretty well. for the most part. And calculus, for example, is based on like the building up of infinitely small things. But we, yeah, it works in practice, but it's not taken seriously when the final prediction is also in. But I think there are places where, like you mentioned, black holes. Black holes won't last forever, but because of Hawking radiation. But that radiation still exists, and that will exist presumably forever. The energy that there is just energy, and it's either bundled up in matter, or it's exists as photons. That that doesn't go anywhere. I mean, the density is changing because space is expanding, but the energy itself doesn't go. So I would say there's one place where I think all scientists believe in some infinity, in the sense of never stopping, which is like the age of the universe, like the length of time the universe will last. We don't have any indication that it's at some point going to stop lasting. Um, and then that I think is easy to conceptualize, right? There isn't like an end. What would that number? Why would they be about what that right? So, um, but it's also certainly plausible that like space itself is infinite. Right? We have an observable universe, and that's just dictated by the finite speed of light. But and we know that there are parts of the universe that uh, are there, but we'll never see it because of the finite speed of light and the expansion of space-time. What's beyond that? Well, I think, yeah. I mean, I don't think it seems consistent, or even. I think it's probably the most comfortable thing in the sense of it doesn't provoke any more questions to say that it just extends forever, like it never stops. Because, yeah, if it stops, that that's a pretty big question, right? Like, why does it stop there? And what's beyond it?
Yeah, I get it. In a way, there's more questions if we assume something other than it just goes on. Yeah, I get it.
Yeah, but I like it how you just explain it, because like it's easier to imagine it, at least for me, that way, where infinity is basically, if I understood you well, something that just keeps going on instead of a number or something that actually exists and is infinite,
Yeah,
which it works better for me that way, at least.
yeah. I mean, there's a that's a very simple like proof, right? So you could say numbers themselves, what counting numbers, 1, 2, 3, 4, 5. Is there an infinite number of? Well, the answer is yes, and the way to prove it is exactly as you said, right? So if there wasn't an infinite number of numbers, then there'd have to be a biggest number. Right?
Hmm.
So let's pick that biggest number. We'll just add 1 to it. So that couldn't have been the
Yeah.
biggest number. Therefore, there are an infinite number of numbers.
Yeah, that actually makes a lot of sense. Yeah,
No,
when you put it that way.
in terms of numbers, it always made sense to me. It was just like trying to figure out where we might encounter infinity in physics, in reality. But yeah, you explained it perfectly. Thank you.
Yeah, well, I think, I mean, it, where there could be, I mean, that's what we attempt to do, and then like going back to reductionism, right? We split the atom and then um, found that it's made of things, and then we split the nucleus and found that it's made of things. Um, it could be that just goes on forever, right? We just require more and more energy to, to continue to split them, and that's kind of like the idea behind string theory. Um, although it's amusing that the claim was like, okay, there's just one more level, but if we could produce enough energy to like split quarks and we found that there are other things down there, why wouldn't we assume that we could split those things as well, right? With even more energy. So I think it's certainly conceivable that you can just keep going, kind of things that happen.
But as of now, we think that fundamental particles are as as low as it
Well,
goes, right?
I mean, I think most people would say that if you could probe these regions, with high energy, uh, extreme density, these sorts of things, if you could probe those regions, we would find new things that aren't accounted for in our current model, right? The standard model of particle physics, which includes the quarks and uh, uh, the four fundamental forces. Um, that that's the standard model because it explains everything within the region that we can probe. So if we can go beyond that region, I think most physicists think that we're going to find. I mean, in a sense, it's hope too, right? They want to find new physics because that's what makes it interesting. But certainly,
Yeah, if we know everything already, I mean, what's the point then going further? Yeah, that makes sense.
yeah, yeah.
I have no more questions.
I
here.
got another one, which is maybe a bit dumb, but I'm gonna ask it anyway. So, if you could visit any cosmic structure or any cosmic event safely from a distance, but see it with your own eyes, what would you like to see?
Okay. Yeah, I like that question. Usually, it's like if there was a person, any historical person, who would you rather meet? I don't like that
Yeah,
question.
something like
Uh,
that, but
yeah,
just like made better for you.
yeah, yeah. uh, I think, yeah. I mean, there's not a lot of options, I suppose, right? When you think of like cosmic events, you think of like the Big Bang, uh, formations of stars, planets. Uh, there's not a lot of like spontaneous events. You have like supernova. Uh, yeah, I mean, you could, yeah, and then get up close to a black hole, something like that. Um, those are all kind of like the obvious ones. Um, I think if it to be at like so you know like this effect of when black holes merge, they create
Hmm.
like this kind of like rippling of space time, which we detected
Hmm.
with detectors in the last, I think it's maybe 10 years ago, 15 years ago for the first time. So when two black holes, or like a black hole and a neutron star, are close to each other, they like spiral around each other. And that, because of their size, affects space time, stretches and distorts it. Um, but the actual like final merger creates like a big effect. And what it does is it sends out a wave that kind of like stretches space time like this, like it goes, like that. And when you have two uh, lasers that are perpendicular, you can detect that what the length of one has shrunk relative to the other one. That's effectively what they do with these giant experiments. But it's so small that you can't feel it, right? You need these enormous lasers and just to see a very, very tiny effect. Um, if you were up close, you'd be ripped apart. But there must be some distance where you could feel it, but it would be safe. And I think that's where I'd want to be.
Yeah, that's awesome.
That's an
That's
amazing
freaking
answer.
awesome.
Yeah, that's an amazing
Yeah,
answer.
I mean, when you started talking like the obvious ones, and I was like, yeah, I would like to see a black hole, but this is so much
No,
better.
but I was stuck at seeing, and the fact that he
Yeah,
came up with an
with
like
feeling.
feeling it,
Yeah.
I just
Yeah, amazing. Chris, this has been a blast. Thank you so much for your time. For anyone who hasn't read or listened to Cosmic Bullshit already, they absolutely should. They should go back to Quantum Bullshit as well. Some of us, I mean, not very happily, but I must admit, some of us started with the Baby University series. So, like, yeah, that might be a place for some of us to start with and then go further on. But yeah, absolutely, you're such an amazing artist, and thank you so much for your time today.
Yeah, thanks for having me.
Thanks so Thank you so much, Chris. Like this experience for the first time talking about all of these things that I love and learn about as a hobby, finally being able to talk to somebody firsthand about some of these questions, amazing experience. So thank you from the bottom of my heart.
Awesome. Thanks, guys.